Hey guys! So today we're looking at Taylor polynomials in Taylor series, day 4. So in class, you guys have previously learned about Taylor series and Taylor polynomials. So if you need to review, just look at the Taylor series video. This is the general expression for a Taylor series centered at x is equal to c. Today we're going to be focusing on the Maclaurin series, which is a Taylor series centered at c is equal to 0.
So we're just going to do one quick example to brush up on the Taylor series. So in this case, it's asking you to find a Taylor series for f of x is equal to e to the 5x centered at c is equal to 2. So what we did first was, because this requires finding the first derivative, second derivative, third derivative, etc., we made a list of the derivative functions, and then we plugged in 2 because c is equal to 2. And so we basically plugged in these values that we found into the expression to find the first 4 terms. So for example, the first term would be f of 2 because it's f of c, and that's where we got e to the 10. Then the second term would be f prime of 2, which is the first derivative, and that's equal to 5 e to 10. So that's where we plugged in f prime of c, and then we also plugged in x minus 2 because c is equal to 2. And so we just plugged into the expression, and then we got the first 4 terms. After finding the first 4 terms, then we went to go find the general term as requested by the problem. And the general term can be found by looking at the expression that was provided and plugging in into the function. So it would be the nth derivative, so we just kept that here, of 2 because c is equal to 2, and then x minus 2 because c is equal to 2 once again, and we just plugged in accordingly. So we got nth derivative of f, 2, and then x minus 2 to the n power, and then n factorial. So we just followed everything that was provided in the expression. And so moving on, we have started to focus on the Maclaurin series. And we need to know 3 special Maclaurin series, and the first of which is e to the x.
Okay, so you would do the exact same steps, except instead of plugging in 2 for c, you would plug in 0 because it's a Maclaurin series. So here we found the derivatives of e to the x, and then here we found them at 0. And so since it's e to the x, they're all the same. And then here we just plugged it into the expression. And so the first non-zero terms we got was 1, x to the 1 plus x to the 2 over 2 factorial, so on and so forth. And then using that, we just found the general term, which was this.
And then basically we followed the expression from above where we had the general term. So we just followed the exact same steps as before. And then this is where e to the x. And then it asks for what values does of x does e to the x equal the series that we found. This is the series that we found, and the values of x are all real numbers. And the way that you can tell is through the interval and radius of convergence test, but we won't go into specifics here because it is in its own video. So continuing on, we have a second Maclaurin series test that is important as well. Our second special Maclaurin series. And this one is to derive a series for sine x. So we followed the exact same steps as before because we did have to list out our derivatives. So we had our first derivative, second derivative, third derivative, etc. In order to plug into the equation as before. And then we plugged in 0 for c because a Maclaurin series is where c is equal to 0. Then after plugging that in, we found the first 4 terms, first 4 non-zero terms. So in our case, f of 0 is equal to 0, so that's why we did not include it here. Then we moved on to f prime of x, and that one's equal to 1. So f prime of x is equal to 1 times x minus 0, so it'd just be x. And that's where we got this value. So we continued the same pattern, and we found our general term by plugging in to the equation or the expression that we mentioned above. And so that is our series here, and that's where, and then we calculated for what values of x does sine of x equal the series that we found, and we got all real numbers, and this is once again following the interval and radius of convergence test. And so we have our third important series for Maclaurin series.
So this is for cosine x. So again, we did the exact same thing. You found the derivatives, first, second, third, etc. for cosine x, which is right here, and then we also plugged in 0 for c because it's a Maclaurin series. And so that's what we got over here, and then using these values, we plugged it into this we plugged into this original expression, and we got these are the first 4 non-zero terms that we got. And then using this, we also found the general equation. And then again, it asked for what values of x is cosine x equal to the series we found. And so we found that it's at all real numbers, again, because of the interval and radius and convergence test.
And so, so as we mentioned, there are 3 special series, and so you can manipulate these series.
So the ways to manipulate these series include substituting into the series, multiplying or dividing the series by a constant or a variable, adding or subtracting 2 series, or differentiating or integrating a series. So looking at an example, we have the Maclaurin series for f of x equals to sine of x squared. And so it asks to find the first 4 non-zero terms in the general term.
And so as we mentioned, you would be manipulating a series, and so we'd be manipulating the sine of x series. So as before, we had our first 4 non-zero terms right here, because we found it using the Maclaurin series, or we used Taylor polynomials to derive this, and so, or Taylor series. And then, so basically what we did is we took those 4 non-zero terms and we substituted x squared for every x value. So for example, the first x value, or the first non-zero term was x, and so in our case, we did x squared because you substituted x squared for every x value. The second non-zero term was x cubed over 3 factorial, and so we did x squared to the cubed and then over 3 factorial. And then we continue that same pattern through these, and that's how we derived our first 4 non-zero terms for the sine of x squared. And so we were able to find our general term by doing the same thing. We would be substituting x squared for the x value, and so rather than going through the tedious task of finding the Maclaurin series one by one as we did before, we could just use substitution in this case. So we'd use our answer to find a Maclaurin series for f prime of x. This is a derivative. And so just like before, how we did each term individually and we substituted x squared for each x value, we would be using, because this is because it's referencing sine of x squared, we would take our sine of x squared values and we'd be finding the derivative of each one. So for example, x squared is our first term here, so we'd get 2x as our derivative. And then the next one, and so on and so forth, we'd be finding the derivative for each term individually. And this saves us the time from actually finding the derivative and then going through the entire Maclaurin series steps. And we found this one by choosing our general term for the sine of x squared and finding the derivative of it. So the way that we found the derivative is 4n plus 2 times x to the 4n plus 1 over 2n plus 1 times 2n factorial. And so this one's just going into detail about how we simplified it, but basically you can cancel out 2n plus 1 and 2n plus 1 at the bottom, and this is how you get the simplified equation right here. But basically all you have to keep in mind is that rather than going through all the tedious tasks of finding each derivative, if you have the function like this and it's asking for the derivative, you can just find the derivative of each term individually and then find the derivative of the general term to save you time.
So looking at another example, here we have Maclaurin series f of x is equal to x times cosine x. So give the first 4 non-zero terms in the general term. So here we would be using the series for cosine x, which is right here. And so since it's x times cosine x, all you would have to do is take the first non-zero terms from cosine x, from the series cosine x, and you would multiply those terms times x, which is what we did here. So for example, the first term was 1, and so multiplying it by x, we just got x. And the second term was x squared over 2 factorial, and so multiplying it by x, you just got x cubed over 2 factorial, so on and so forth.
And then we'd be going on to find the general term, and similar to how we found the derivative of the general term to get in the previous problem, we would just be multiplying x by the general term, because in our case it was x cosine x. And so the next part of the problem is using your answer to find a Maclaurin series for the integral of from 0 to x of f of t dt, or just reading this exact problem, I would be giving the first 4 non-zero terms and the general term. And so in our case, we would we would be taking the integral of each of the specific terms above. So we'd integrate x, and that would be x squared over 2, and then we'd integrate x cubed over 2 factorial, and that would be x to the 4th over 4 times 2 factorial. And we're basically just following the same integration techniques as we have learned previously in calculus. And we would do it for each term. And once we do that, we'd also use the same integration technique for our general term. So we would integrate our general term to derive this, we'd integrate this general term to derive this term. And this is how we created or we found our general term for the integral. And so in total, this is our video over Taylor polynomials and Taylor series day 4, and we basically went into detail about the Maclaurin series. We reviewed over the special series that you guys need to keep in mind, the e to the x, sine of x, and then cosine x. And then we went into detail about how you can manipulate these so you can save time on the questions that are a little harder, such as x cosine x. So instead of actually having to do step by step where you find the derivatives and going from there, you get to save time by simply finding or multiplying by x.